Okay, in this video, we're going to talk about something called the rate of heat transfer. So what I mean by that is, you know that we lose heat maybe through the walls and the windows of our house in the winter time. We also know that we lose body heat when we go outside in the winter time due to the coldness. But if I put on a coat, then maybe I don't lose as much heat in my body as I maybe do through my face or my head that is not covered, or if I don't have a hat on or something like that. So what we're trying to do here today is we're going to try to calculate or approximate the rate of heat that is transferred in certain situations, and also be able to use this information to make some better educated decisions in the things that we do in our everyday life. All right, so the first thing that we have to do is every time we talk about the word heat, I think what comes in people's minds is the concept of temperature, which is different. So temperature is the measure of the average kinetic energy of the particles that make up a substance. So I want you to think of like a beaker of water. So it's a bunch of water molecules and they're all bouncing around. And because they're bouncing around, they have kinetic energy. That's the temperature of the water. If I heated up the water so that the temperature was higher, then they would be bouncing even more. They'd have even more kinetic energy. So kinetic energy is what relates to temperature. So we're not talking about temperature today. We're talking about heat. And it says heat is the transfer of energy due to a difference in temperature. So the concept of heat is the transfer of energy. So every time you see the word heat, I want you to think that we have like substance 1, we have substance 2, and I'm going to go make an arrow. That's heat, the transfer of energy. So the variable for heat, confusingly, is Q. All right, so Q stands for heat. And the units of Q are going to be joules, because heat is going to be a form of energy. In English units, which are sometimes called imperial units, the unit for heat is BTUs. And we actually talked about BTUs already once this school year. We said that barbecue grill, how the ability to cook your hamburgers is measured in BTUs. Today's lesson, though, is the rate of heat transferred. So rate means like per unit of time. So the rate of heat flow is going to be Q over T, like how fast the heat flows. And so then my units would be joules per second. But what we're going to find out here later is in imperial units, it's more common to do BTUs per hour. And we may end up having to break the video in two, and if we do so, the second video we'll talk about the BTUs per hour. All right, the rate of heat transfer equation looks like this. Instead of writing it on the line, I'm going to write it down here in this spot. So first of all, it's not just heat transferred, it's rate of heat transferred. So therefore, it's going to be Q over T. That's the rate of heat transferred, equals, and here's the equation. It's a lowercase k, a capital A, a delta T over an L. So first of all, when I was in college and I had to memorize a whole bunch of physics equations, and my mind was getting full, I looked at this and I said, wow, that looks like the word cat. C or K-A-T, cat, with the tail, like this little tail, cat with a tail. And that's how I memorized this equation, cat with a tail. And look at my cat, there's cat, and then there's this little tail. His tail looks like an owl. It's just so perfect. Cat with a tail. All right, so K-A delta T over L. K is going to be like some sort of constant. And K stands for thermal conductivity, and it depends on the substance. So on page 3 of the notes here, you'll notice that different substances have different K values. So you're going to have to look up the K values. A stands for the area. And so the area would just be the length times the width, where you have to measure the length in meters and you have to measure the width in meters and then multiply them, so we'd have meters squared. Delta T is going to be the change in temperature, just like it was in our last topic of expansion and contraction. And technically it should be the change in temperature in Kelvin, but as we discussed, the change in temperature in Celsius and the change in temperature in Kelvin is the same number. So therefore, as long as you use consistent temperature values of Kelvin or Celsius, either one will be fine. L is the one that confuses people sometimes. L stands for thickness. So like when I say thickness, let's pretend that this is a door. So it's got length and it's got width, so it's got area, but the door actually has some thickness. And so this thickness is L. Or if I had a pane of glass, like how thick is that pane of glass? That's L. And L also has to be measured in meters. Okay, so let's go back to the K. What does it mean if K is large? It means that heat is going to be transferred very quickly. So when I look at this chart, what substance transfers heat the quickest? Well, in terms of our chart, that would be silver. And what does it mean if K is small? It's more apt to retain heat. So what does not transfer heat very well? Air, goose down, and that'll make a little bit more sense here in a minute. All right, so to try to make some sense out of these K values, I have two examples here that I want to talk about. So my first example is going to be, we're going to pretend that you want to make macaroni and cheese for lunch. Not the microwave kind. The kind you got to boil the water and then pour the noodles in. All right, so you want to make macaroni and cheese for lunch and you're super hungry and you want it to happen fast. So what kind of pan would heat up the most quickly? We want something that transfers heat quickly, that goes from the burner and it goes right through the pan to the water to heat up the water. So if these were my choices of pans, I had a copper pan, and an aluminum pan, or a stainless steel pan, whatever would have the biggest K value is going to heat up the most quickly. And then you say to yourself, well, copper isn't a kind of pan. Well, first of all, there are copper pans. A lot of people like maybe hang them above their kitchen island. They're kind of decorative. And they're super expensive. You know why they're expensive? Because they work the best. Other times you may have seen pans that look like this. I'll call them stainless steel pans. But they have a little band at the bottom. And this little band at the bottom is copper. Those are good pans because the heat's going to transfer through them very quickly, and you're going to make your macaroni and cheese faster than somebody who's using an aluminum pan or a stainless steel pan. In fact, you know what? Stainless steel does not heat up very quickly. I remember that every Thanksgiving when I use my big stainless steel pan to make mashed potatoes, and the potatoes take like an hour to heat up. All right, so I make my macaroni and cheese, and then I want to put a lid on it so that it stays hot for as long as possible. So what kind of lid would retain the most heat? So now I want a small K value because I don't want heat to transfer very quickly through the lid. And so putting a stainless steel lid on a pot is smarter than covering the pot with some aluminum foil because stainless steel has a much lower thermal conductivity than aluminum. All right, now let's think in the opposite direction. All right, so first of all, now we're going to pretend it's winter time and it's a cold winter night. It says, what do you want to cover up with on a cold winter night? You're laying in bed. What do you want to cover up with? We need a small K value. You know what you want to cover up with? Air. Air. No, I'm not talking about like just plain air. But when you see air in a thermal conductivity table, it means air embedded between something else. So what if I had like a piece of material, piece of fabric, another piece of fabric, and a little bit of fluff in between. Okay, a little bit of fluff. And I say a little bit of fluff because really what I care about is not the fluff. I care about the air. You know what this is? You know I just drew a picture of? This is a comforter. I want to cover up with my comforter. It's got two little pieces of fabric. Okay, that's not keeping me super warm. It's got a little bit of fluff. Honestly, that fluff is not keeping you warm. The particles of the fluff, what's keeping you warm is the air pockets that are in the fluff. So yeah, I'm going to use my comforter on a cold winter night. What kind of coat do I want to wear if I go outside in the winter time? What kind of coat? Well, I could wear a coat that's puffy, a puffy coat that's like a comforter. Again, there's air pockets in that puffiness. I might wear a goose down coat. I might wear a wool coat. Okay, those are all good ideas. I am not going to wear a silver coat or a copper coat out in the winter. That would make me very, very cold. Why do drapes in front of a window reduce heat loss? Drapes. So I'll draw a window here. And when I have my drapes in front of the window, there's an air pocket between the drape and the window. So if I have all my drapes closed like this, again, it's kind of like the comforter, and the fabric itself, especially if it's a thick fabric, can be insulating, but on top of just the insulation of the fabric, you have the air pocket that you've created as well. So that means hang your drapes a little bit out from the window, not smack on top of the window. All right, what are thermal paned windows and why are they helpful? Thermal paned windows. So a lot of times, I'm just going to draw the side view. A window is like a piece of glass. And that's actually not a very good piece of glass, or not a very good window. But a thermal paned window is that you have another piece of glass. And so inside your two pieces of glass, so your window is kind of like double thick, is this air pocket here inside. And again, air is very, very insulating. Okay, so now let's try to put this into something a little bit more mathematical. All right, so my example here is going to be a door, a thick wood door. So I'm going to draw a thick wood door. And I went on the internet and I looked up, like in our real life, you know, what is the standard dimensions for a door? And it said that doors are normally about 36 inches wide, but we have to do things in meters, so I converted that to meters. So the width of my door is going to be 0.9144 meters. Doors are typically 80 inches tall. That turned out to be 2.032 meters tall. And they come in a variety of, obviously, thicknesses, but I picked a door that was 2 inches thick. So the thickness over here, remember thickness is L, is going to be 0.0508. All right, and now we are going to pretend that inside the house it is 72 degrees Fahrenheit. Well, I have to convert that into Celsius, and 72 is 22.22 degrees Celsius. And so that's inside the house, 22.22. And then outside the house, we'll pretend it's 40 degrees outside the house. So that turned out to be 4.44 degrees Celsius. So because I have a temperature differential, because it's warmer in the house than outside the house, there's going to be heat loss in this direction, going out of my house. So not only do I care about the heat loss, I care about like how fast that heat loss is happening. So that's why it's Q over T. So our cat with a tail equation. And we have a wood door, so I'm going to look up in my chart wood. Wood is 0.17. Wood is pretty insulating. That's good. And the area then is going to be the length times the width. So 0.9144 times 2.032. And then the temperature difference, 22.22 minus 4.44, turns out to be, I'm going to squish this right up here, 17.78 over the thickness, which is 0.0508. And then when I number crunch that, I end up with 110.5 joules of heat per second. I lose that many joules per second through my front door on a 72 degrees inside my house and 40-degree day outside. All right, I'm going to stop this video now because it's getting long, and then I will talk through the last two on the second video.